Okay, so today we're going to continue on the one-way repeated measures. And this is where we're at now. So this quarter, we started off with one-way ANOVA. So it's basically looking at mean differences among groups. After that, we did factorial ANOVA, which is having more than one IV. We had example with two-way ANOVAs and three-way ANOVAs. And then now we're at repeated measure. So each case is measured more than once. So that's the essence of repeated measure. And so today we're going to talk about one-way repeated measure. And then after that, we're going to go into factorial repeated measure. So we're going to move towards to having two variables in a repeated measure study. So before we go into running SPSS, I'm going to talk about the assumptions of repeated measures. So this will be quite similar to what we've been doing so far with a slight difference. So this is a review of what we had for one-way ANOVA and factorial ANOVA. So we had 4 different criteria or assumptions that we had to test. One is normality, and one is independence of error. This is more on the research design. We didn't really actually statistically test this. And then homogeneity of variance and absence of outliers. So these are the 4 that we did previously for the first 2 units. And so for repeated measure, we have similar 4, but we replace independence of error with sphericity. So I'll talk more about what's sphericity, but first I'll talk about some slight differences between normality, homogeneity, variance, and absence of outliers. So normality, I don't know if you still remember what we did was there was a robust criteria. If it was equal sample size, no outliers, two-tailed, and had more than 20 in terms of degrees of freedom, it was robust. We didn't have to test for normality. And so for repeated measure, actually it's even more simple than that. So for factorial design, do you remember that we split the file, or based on your homework, based on the 2 IVs? And then, so we had the 6 cells, or for the 6 cells. And then we tested normality for that, each cell, if we were to test. But for this, we only have one value in each combo of case and IV. So because now, one of the so this is, so this is, IV1, IV2, IV3, and then we have the different subjects, subject 1, 2, subject 3, subject 4, and then they have all their different numbers, scores here. And before, we would split them by the groups. So depending on which participants are in which group. So now, each participant, there's no groups. Okay, so each cell is only one variable, right? So for this, each cell is only one variable, so it will be equal sample size. Sample size will be 1 across each cell. And then there's no outliers because one variable there's no other outliers. So for normality from now, for the repeated measure, it's okay if it's the degrees of freedom for error is over 20. So we're good. So we don't need to worry about equal sample size or outliers. As long as the degrees of freedom of error is over 20, normality is robust. And similarly, homogeneity of variance. If we were to split this into cells, these each are a cell in itself. So what we're going to test instead for homogeneity of variance is the variance of the IVs. So the IV one, like at the IV at the different levels. So time 1, time 2, time 3. So we get a variance for time 1, get a variance for time 2, get a variance for time 3, and then do the Fmax. Does that make sense? So in the past, what we did was we split this file by their grouping, or the cell, and then we get the different variances. Now we don't need no more splitting. We just get the variance of the the variables, and then do the Fmax. And similarly for outliers, we look at outliers for the variables at the different levels. And if there's outliers detected, this is what the different options that we can do. One is we can delete the cases with outliers. Let's say variable number 3, case number 3 had an outlier here. One way is to take it out, but of course we'll just be removing the whole case. And the other one is we can transform the scores. So if there's an outlier here, we can transform, but if we transform a certain variable, we transform the whole DV, the DV for all of the cases. So don't just transform the one that's an outlying variable. So if we only transform one, for instance, we do square root, then it would be on a different scaling as the others. So make sure that if we do transformation, it's the whole set for the dependent variable. And then the third option would be we can adjust the outlying scores to make it, if it was extremely large, to make it still the largest but not as extreme. So those are the different options for absence of outliers. So these are fairly similar to what we've learned for factorial design or one-way ANOVA, just that we look at the variables itself without any splitting. And the new one here is sphericity. So we're no longer needing independence of error, because independence of error is automatically violated in repeated measures. So because we are reassessing the same case over time, so they are the same case, they're not independent from each other. In the past, when we did one-way or factorial design, each score represented a different case. So they were independent from each other. But that's no longer the case here. And then there's effects over time. So effects on the cases, on equipment, testing situations they're likely to drift over time if we're doing an experiment. So for example, if there's equipment, they might get older, whatever, depending on the type of equipments. Testing situations might be different, or like the RAs running the research, they might be more efficient. And so there's going to be effects that accumulate over time. And also, there's similarities in the different levels of IV. Higher correlations among more similar levels of IV, such as closer in time. So for example, scores on time 9 and time 10 might be closer to scores on between time 1 and time 10. So they're not independent anymore. So we're not going to look at independence of independence of error. Instead, we're going to look at sphericity. So sphericity is an assumption that combines independence of error, homogeneity of covariance, and additivity. So it's pretty sophisticated, and to be honest, I don't know what they all actually entail, so don't worry about it. And what we will be doing is we will look at Mulchley's test of sphericity. So when we run SPSS, Mulchley's test of sphericity will come out. We just look at it and see if it's significant or not. So if it's significant, it means that it's violated, and then we have to make adjustment. But if it's non-significant, then we're good, and we move on with sphericity assumption assumed. So it's kind of like the Levine's test of homogeneity of variance. We just take a look, see if the p-value is significant or not, and then based on that, decide the next step. So when sphericity is violated, here's some options. So one option is to use one type of epsilon adjustment. So there's going to be 3 adjustment methods. One is the Hume-Felt, is less conservative and preferred, and Greenhouse-Geiser in lower bound. Lower bound is the most conservative. Most conservative means that it adjusts stricter, so it's harder to get a p-value, a significant p-value. And so these are three options, and for the sake of homework assignment or test, this would be the one that's preferred. So give you a hint, I think in the homework assignment it will be validated. And so make sure you look at this instead of the surficity assumed one. And for multivariate test, okay, another alternative option is to use the multivariate test results to look at the mean differences. And you would look at the Wilks lambda there. So, and before we end, just a few conceptual issues. So I think we did talk about the sequence in terms of like receiving different types of therapy. And if you receive psychodynamic first and CBT second, there might be an influence or carryover effect of the treatment effect of the first. And so if we wanted to control that, one option would be to counterbalance that, to have some people have treatment 1 first and then treatment 2, and then some people treatment 2 first and then treatment 1. So it would balance that sequential order effect. And another issue related to repeated measure is missing data. So if we are tracking people over time, it's likely that they participate in time 1 and then they no longer participate in time 2. And then, or they come back at time 3. So we're gonna have missing data, or it's very likely that we're gonna have missing data. And that's not just like they didn't pay attention, it's because they didn't show up. And so there's different ways of dealing with missing data. One way is to just simply delete the case. So if they have a lot of missing data, we delete them. Or we can say if they have how many % of missing data, we delete them. Or if they have any missing data, we just delete them. And so for example, if this was a data set, and let's say this is 4, 5, 3 missing, 6 missing, 2, 8, 1, 5, 7, 3. Okay, so we have a few missing data here. And so there's different ways. If we delete cases with any missing data, it will leave us with only one case. And so, 2 case, subject 1 and subject 3. And, but we also lose the value of these that they did fill out for case number 2 and number 4, and it will decrease our power. So that probably wouldn't be the way to go. And so other ways of dealing with these 2 missing data is to estimate the missing value and replace it to make a guess. So I think some people are like, what?
Sorry, yeah.
So you feel weird. What do we average? Do we average across here or do you average across here? Because it's reasonable to use an average score. Okay, so for example, we can look at, okay, on average, how did people score at time 1? And then use that average and replace this missing with time 1. And then this, we would average these 3 and then get the score, estimate the score for that. So that would be one way of averaging. That would be averaging based on series mean. So the average of that variable. But we can also say it's more strongly influenced by the individual. So maybe we should average their scores and then replace the missing with their own scores estimated based off of time 2 and time 3. So that's another way of replacing this value. So simply using the mean for that value, we could use the mean of that individual or the mean of that IV. These are 2 different ways of doing it. Okay, the next thing is regression or expected maximization. So that's the regression is sort of using some kind of formula to combine both. So it takes into account this reviewer is more strict, and takes into account what the other reviewers have rated, and then estimate the score. So that's more of a regression or expectation maximization method. Okay, and then there's also, you'll see, if you see an article that they say missing data was replaced by multiple imputation, what that means is that it uses different subsets of the data, and it estimates the score, and you estimate it like 10 times. And then you take all the 10 estimated score and get the average. And then it's more accurate, it's based off of more random sets of data. So that's another way of doing it. So I think so far, I've been asked by a reviewer, like, okay, I just want you to use multiple imputation. And that was a pain. So I had to run it several times and then calculate the average and then replace it. And yeah, so, but it should be more rigor. And then there's also another one I didn't list. It's called FLIM. No. Full Information Maximum Likelihood, FIML. And that's, as of now, that's the most rigorous missing data replacement. But SPSS doesn't have that function. So if you want to do that, you would have to use M+ or other software. But it's called Full Information Maximum Likelihood. So those are different ways of replacing missing data. You don't need to know all that. I think when we go through the data set that we collected, we'll talk about what we want to do with missing data. So in reality, it's not going to be all clean like the sample data sets that we practice in class. It's going to be like, oh, there's missing here, there's that and that. And so a week from today, so next Monday, I'll use a data set that you collected, and we'll talk about how to clean data, how to manage, how to give the variable names, and then prep it ready to run the analysis. So it's been really easy in terms of clicking the ANOVAs. It's more of a matter of a few seconds of selecting what to do. And usually I spend more time cleaning the data than running the analysis, but we'll go through that next week.